Hey everyone. Today we're going to be working on the Unit 8 FRQ, the 2010 Form B number 1. I have to say, first of all, that this question was developed before the new exam format came. And so even right away when you start off with this first question, they're going to ask you about two structures. I do not think that they would give you a question like this anymore where you have to know organic naming because they took that off of the test requirements. So where it talks about N-butane and isobutane, and they're like, oh, just draw those Lewis structures, and you're like, super, definitely don't know how to do that. I think what would happen now is on the test, instead of just giving you a blank space like they do in this problem, I think they would give you like a different structure or like partially drawn structures and go from there. So if you're looking at this and you're like, I don't have any idea how to do this, that's because we didn't learn it because they don't expect you to do that anymore. But you should be able to draw at least one of those Lewis structures. So if we look at C4H10, oh, I guess I should go back. We'll start the problem. So a compound butane, C4H10, occurs in two isomeric forms, N-butane and isobutane, 2-methylpropane. You're like, oh great, don't know any of those words. Both compounds exist as gases at 25 degrees Celsius and 1 atm. So for A, it says draw the structural formula of each of the isomers, include all atoms, and clearly label the structure. Again, I don't think they're going to expect you to do something like that, but we'll go with it anyways. So C4H10, remember with all Lewis structures, you need to figure out the number of possible electrons that you can put in your drawing in the first place. So we have 4 C's, each of them is 4, and so that's 16 electrons. We have 10 H's, and that's 10, so our picture needs 26 electrons in it. My first inclination is to just draw a bunch of C's in a line. And so I'm going to do that. Connect them with H's. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And if we look at that, everything has the number of valence electrons and electrons in the picture it's supposed to, so let's check and see if everything works out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 bonds. So that's 26 electrons, and we've got nothing left. So in my expectation, if you could draw this, that would be great. An isomer is just the same chemical formula, but with a different Lewis structure. My first gut instinct when I draw this is to take the C and branch it off. I can tell you that if you go like this, and then let's say you turn a corner like that, that does not count as a different structure because it's all connected in the same way. But if you look at this Lewis structure, we have a little bit of a different connection going on because it is off the center carbon. So there's kind of like it's almost got like a trigonal planar shape to it. So what I'm going to do is put my hydrogens on. And there's my second isomer. So in this case, like I said, you're not going to be expected to do something quite this complicated, but here are your two Lewis structures. This Lewis structure here is butane, and this Lewis structure here is the 2-methylpropane. Again, organic naming is not on the test, so you do not need to worry about that any longer if you're freaking out about that. All right, for B, it says, on the basis of molecular structure, identify the isomer that has the higher boiling point to justify your answer. When we talk about Lewis structures, the size, the physical space a molecule is going to take up will affect its intermolecular forces. And physically, the larger it is, the stronger the intermolecular forces are going to be. So in the case of these two Lewis structures, because this is 4 carbons long and this one on the right here is only 3 carbons long and it's kind of more compact, the one that's longer is going to have the stronger intermolecular forces. So what I would say is that N-butane will have the higher boiling point because it is less compact than the 2-methylpropane. I'll say larger, less compact molecules have more areas to interact. So they can have stronger London dispersion forces. Which lead to higher boiling points. Okay, so that's generally how it goes. If you have a molecule that's really kind of long like this, not only are you dealing with usually more intermolecular forces because you have more electrons, but in this case, the actual physical size of it means that there's more places to interact, and so you have stronger London dispersion forces. Okay, moving on. Here we get to the Unit 8 content. It says 2 isomers exist in equilibrium as represented by the equation below. N-butane going to isobutene, and they give you the K. Suppose that a 0.01 mole sample is placed in an evacuated container at 25 degrees. C, write the expression for the constant. So it is, products over reactants. So I'm going to go Kc is equal to concentration of isobutane over concentration of N-butane. And that is equal to 2.5. So it's just the K value. You don't even need to put the 2.5 there. I just did that because I feel fancy, I guess. Okay, D says to calculate the initial pressure when the N-butane is first introduced before the reaction starts. So it tells me in the problem I have 0.01 moles of N-butane in a 1 liter container at 25 degrees Celsius. So holy moly, this feels like it's going to be an ideal gas law problem. Okay, so we know PV equals nRT. If we're trying to solve for P, it is equal to nRT over V. And so we are going to plug things in. My number of moles is 0.01 moles. R is always 0.0821. Oh, I wrote that wrong. Atmos liters per molk. Temperature, don't you dare forget to put that in Kelvin. It's 25 degrees Celsius, so that is 298 Kelvin. And then we're going to divide it by our volume. And I'm going to accidentally cross some stuff out there, and the volume is 1 liter. Excuse me. When I put that into my calculator, hopefully you put it in correctly. You should get 0.24 ATMs worth of pressure. Okay. For part E, it says the N-butane reacts until equilibrium has been established. Calculate the total pressure in the container at equilibrium. And then it says to justify your answer. So in this situation, if we look at our equation, because it is a 1-to-1 mole ratio, it kind of doesn't actually matter what is going to happen inside your container. So what'll go on is that as some of your reactants turn into products, the pressure of the reactants is going to go down, but at the same time, the product pressure is going to go up at the same amount. So what I'm going to do is I'm going to talk about the 1-to-1 mole ratio and how it's going to keep the pressure the same. So I said because the reaction occurs on a 1-to-1 ratio, as the pressure of the reactants goes down, the pressure of the products goes up at the same amount. This leaves total pressure at 0.24 ATMs. There was an FRQ that we talked about at in equilibrium before we went on this little hiatus of seeing each other, where it was a 1 to 2 mole ratio, and so then the pressure would double if it would have gotten all the way to the end point of the reaction. But in this case, because it's a 1 to 1 ratio, no matter what, whether I'm at equilibrium or completely at the end or whatever, the total pressure is still going to be 0.24. If it's not a 1 to 1 mole ratio, then you have to do an equilibrium problem, and they're going to get to that in part E2 here.